Next up, we have David Lucsányi, and he's going to talk about Puli Lunar Water Snooper, an in-situ water mapping payload for lunar surface missions. David.
Hello. I share my screen. It's okay. Can you see it?
Yes, we can. Yes.
Perfect. So, hello, my name is David Lucsányi, and I'm the lead payload scientist of Puli Space Technologies. And I will present you the Puli Lunar Water Snooper, the water mapping payload we are currently developing. And I would like to thank the organizers that the opportunity I can give this talk here. This week and also in the last couple of years, we heard a lot of people mentioned many times the challenges of the lunar radiation environment, and also the urgency, the fact that we should explore and map as soon as possible lunar water ice. So we are working on this exactly. So just a very quick introduction to the radiation and the neutrons on the lunar surface. So the lunar radiation environment is a mixed radiation field, which means all sorts of different high energy particles are coming from all the different directions continuously. And on top of that, it has a very high variations and dependence both in time and on location. But the primary source of radiations are galactic cosmic rays, as you may know, and these are continuously bombarding the lunar surface, producing high energy neutrons, secondary albedo neutrons in the lunar regolith. These neutrons are scattering around, and by scattering, we are losing energy. Some neutrons may lose more energy, some may lose less energy, but at the end, those neutrons which can reach and leave the lunar surface from the regolith, these have a unique energy distribution spectrum, which contains essential information, highly depends on and therefore characteristic to the subsurface regolith composition. So basically, that's the main reason we can and we should use neutron spectroscopy on the lunar surface. So, fortunately, it is already possible to accurately and realistically model the lunar radiation environments. So that's the reason we are working on this field, and we gained quite a lot of knowledge and experience during these in the last few years. We are performing Monte Carlo particle transport simulations with widely used reliable Monte Carlo codes. This basically means that we are following the trajectories of billions of particles, in this case neutrons, and how they interact and to get basically the final energy distribution when they are leaving the regolith, what you can see here plotted as well. So, of course, these can depend on many different things, parameters, like it can depend on solar activity, also on regolith composition, water ice content, depth of an ice layer, and so on. So we are also studying these. But let's focus on water content of the regolith. So if we increase the water concentration in our lunar regolith model, then we can see that the thermal neutrons, the number of neutrons in the thermal energy range increases, while at the same time epithermal neutrons, the flux of epithermal neutrons are decreasing. So this gives us a very good method to actually measure the hydrogen concentration, just only detecting different energy neutrons. So as we could see, by detecting neutrons, lunar subsurface water resources can be mapped spatially. So here I show an example that I created a theoretical water ice map on the lunar surface and plotted below the hydrogen concentration in function of the rover path traveled. So on all the locations, based on our simulations, we can obtain the thermal neutron flux and epithermal neutron flux above, on that point, that location of the map, varying in water concentration. So as a consequence, we can also, if we could design a payload based on this and send it to the moon, mounted on a rover, which moves around, and we detect thermal neutrons and epithermal neutrons with this payload instrument, we can directly obtain the unknown water concentration of the regolith below and around the lunar rover moving around with this payload. So what you can see here is these are basically the data products of our Puli lunar water snooper payload. So it will continuously transmit back to Earth 3 particle flux values and water equivalent hydrogen concentration values in every 10 minutes or even less. So, but to just a bit give a bit of a context here, how we started and where we are now. So we started the development of this payload exactly 1 year ago, when we learned about the Honey, I Shrunk the NASA payload challenge of NASA via the Heroics platform. And this first challenge has the goal for the teams to design miniature NASA payloads to be used by NASA in future CLIPS missions, for example. So we submitted our concept and won the first prize on this challenge. And then NASA invited us to participate in the sequel of this challenge, which is divided into 2 phases. The first phase we also already won, and therefore NASA is supporting the development of our payload for a 1-year period. The goal of this challenge, the second phase, to build 3 working flight-ready prototypes and deliver these to NASA JPL by the end of January 2022. So, as you can see, the timeline is quite tight and ambitious, but it's still feasible. Last month, we have performed our proof of concept test, so we reached the technology readiness level 4, and now we are in the middle of the payload design review, and soon we can start the functional testing of our engineering models. By the end of January 2022, we would like to reach the technology readiness level 6, sending our payloads to NASA, where they will do their own qualification test, and if payload passes this test, we are eligible to win the second challenge we are currently participating in. And of course, and after that, it's important to mention that NASA would like to send one of these winner payloads, hopefully ours, to the moon during CLIPS mission in the following years. So some words about the main payload specifications. So our payload is really a miniature payload. It has extremely small dimensions, only 10 by 10 by 3 centimeters, and it's less than 400 grams in weight. It requires low voltage and low power. It has a relatively wide operating temperature range. The payload has a quite robust communication interface. We are currently estimating that payload needs around 30 minutes data acquisition time per location. But of course, we could improve on this, and we will. Single measurement will cover few square meters of area and max 1 meter subsurface depth in the regolith to obtain one average water equivalent hydrogen concentration. Ideal host crafts are rovers and micro rovers. So this payload was by default designed for micro rovers in the challenges, and of course it should be mounted on the bottom side of these rovers. As you can see, we established quite strong partnerships with the Hungarian companies in design and manufacturing. And also I would like to emphasize that this is a commercial off-the-shelf component-based system, payload, which means that it's low cost, and future potential users of this payload can have not just a single Lunar water snooper, but even tens or hundreds of them, just to cover a much larger area on the lunar surface during the mission. Okay, but how we can detect those neutrons with this payload? So our main and novel idea here is to use commercial off-the-shelf components, especially commercial off-the-shelf CMOS active pixel sensors as particle detectors. So because these image sensors, what everyone can find in any camera or even phones, the sensors are sensitive not just to light, but also to ionizing and even non-ionizing radiations as well. Of course, in case of low energy neutrons, it is probably it's not enough. So we have developed special coatings for these image sensors in order to enhance the neutron detection capabilities of the sensors. We have 3 sensors per payload, one for thermal neutrons, one for epithermal neutrons, and one as a reference sensor to measure background radiations, which is mainly cosmic ray fluxes. As an example, I have here 2 neutron-induced particle tracks captured by an image sensor during our first irradiation test. So a few words about our first test, which was the proof of concept. So basically, our neutron detection technology and basic payload concepts have been demonstrated already with the radioactive neutron source at CERN. Here you can see a photo of one of our setup, and I've plotted the detected fast and thermal neutron count rates in the function of camera source distance. And it decreases as we move the cameras further and further away from the source. And it decreases the same way as the total neutron flux leaving the neutron source. This perfect proportionality demonstrates that we have successfully measured both fast and thermal neutron fluxes using these modified commercial off-the-shelf cameras next to the neutron source. So, the next neutron test will be with the engineering model of Puli water snooper, and these tests are done in a close collaboration with the CERN and CERN Radiation to Electronics project, where we are investigating the potential terrestrial applications at CERN, for example, as a neutron flux monitor in the tunnels of the Large Hadron Collider. And with this, I would like to end my presentation. And if you have any questions, please let me know in the chat or via email. And thank you for your attention.
Thank you so much indeed, David. There are questions for you in the chat, but for the sake of time, I have to move on, I'm afraid. There's been lots of activity on the chat, including one question from some poor anonymous soul who wants to learn how to become unanonymous, and I'm sure somebody from the tech team will help you there, if not one of the fellow chatters. So I'll let you hop onto the chat, David, to answer the questions for you.